Welcome to our middle school teacher professional development for summer 2024. My name is Sarah Nern. I'm K-12 Outreach Coordinator with the Department of Chemistry.
I'm Stephen, K-12 Outreach Coordinator, Department of Earth, Atmospheric, and Planetary Sciences. What else?
Yeah, I think we're just going to jump to it. We have for today our title, we are Unraveling Earth Secrets with Radiometric Dating.
All right, so we're basically going to have three different, I want to say supplemental activities, is that the right word? That we're going to go through that we've come up with and put together and we've taught. And well, we've adapted a little bit since we've taught it a few times, some of them. The first one is I introduced this when I first started this. I started this with Geologic Time Scale, and I started Geologic Time Scale with personal timelines. And so I would first ask the class, and we'd list on the board, what are some events that has happened in our lives. And so I'd list 5 or 6 on the board and kind of help them come up with it. Sometimes they're just like, look at you and not sure what you mean by that. Usually someone will say something. Sometimes it's random and we'll ask, does that happen in all of our lives? And we use like, did we all start kindergarten? If it's a class, it might not be the exact same year, but it's pretty close. Mm-hmm. And so we can use things like that, do 5 or 6 of those. And I'm guessing a lot of you already do either like this exact thing or something similar to it, but this is the lesson I was taught for that. But and then talk to them about, hey, everyone likes to organize things, so we're gonna arrange this into like a timeline of events for our lives. And so I will up on the whiteboard. I want to say chalkboards so badly, but they took away all my chalkboards, now I have whiteboards. And
damn, you're old.
Yes, Bill. I have several chalk chucks with my name on them. Shut up.
I didn't have my name on.
Well, I had a drum. I put my name.
Oh,
so people like you didn't steal it. Well, people like Bill didn't steal it. He would before you would. But never trust Bill Bay at the pin, by the way. And so, but we would write these. I'd do a timeline, draw a line across the board to do a timeline. I always have like a meter stick out when I do this. And I make increments in there with the meter stick, not in your face doing it, but obviously they're seeing that because I want them to understand that a timeline it's not these random numbers on a line. I want them to understand that a timeline has, what's the word I'm looking for?
Like units?
Units, increments, yeah. We'll use both those words. Mm-hmm. Yeah. And so we'll do that. And so we'll make a little timeline of the events we talked about. And then we'll talk, and I put on this page some vocab words, and the vocab word will be in bold, then the definition there, chronology, organized events in order. That's what we're doing. Then we can introduce a time scale. A time scale, the scale used to represent periods of time, quite simply. I do journaling when I teach. Whenever I taught, I was at a science journal. And so at this point, I would have them doing either that or homework, which I think I always did it in the class, this part. Have them draw one and use, I say rulers, but to be honest, a lot of times I made up some rulers and they were just pieces of paper that I taped over because we didn't have a class set up. Yeah. And it didn't have numbers on them. And I didn't care if they didn't have numbers, they were even spaces. That's all I cared about. And so I'd made up some I had them use for that. And then I'd have them use 3 events from the class, and then at least 3 events not in the class. So it was part of their time that they could put in it. And this worked pretty well. I know the first time I did it, it got a little awkward because our students have had a lot of things in their lives. And when a student talked about having a parent die earlier that year, it's like, well, that's definitely something that should go in your timeline. And so that brought up some more class conversations that I didn't expect the first time, but that's been quite a few years ago. So I kind of expect those a little bit better now. But just be prepared. You have no idea once they start, hey, can I put this in and that, where they're going with that. So if you've not done that, now have them talk about that. Remember, they come up with the craziest things.
Can I just throw in there too, when you had started, I think the first time I had ever seen this lesson is when we did this with students.
Yeah.
And so I think we were going into like, we started at present day.
Mhm.
And then we were sort of going backwards.
Counting backwards.
And then we got to where they were born. A
Uh-huh.
lot of them were born, but then there was still a lot of the time scale left. And when I first saw this, I thought, oh no, our time scale, we still have, we didn't quite line this up. And then I realized, oh no, time didn't start with the birth where they were born. Like
Yeah.
time, there was a whole world before it had happened. So
The only endpoint we have is today.
yeah.
Everything happened before us.
Yeah.
What's up, Bill?
One thing that you said right there, which I've seen you do this a couple times with kids, but when you mentioned that, what a great way to get to know kids, some things about them personally. I mean,
Yeah.
without like,
If you want to or not.
right, but without prying. I mean, it's not like you're prying, they just bring it out, and that's kind of cool.
Yeah.
Yeah. All right. Someone asked if they could have, or where the link was. So yep, there you go. Sorry. And we'll jump in and out, share the links. And they're live web pages, all these, but there's not like links from our things yet because we didn't want to like kick it out until we did the professional development here. But and so then, whoops, I'm jumping down. And then after we do that, we kind of have an idea of time scale and timelines at that point. And so our whole idea is we're getting into the geologic time scale. Now we can, and right here's the link to that big complicated picture that from the international whatever they're called. I can't remember, and I should know this because I had faculty that was on this committee for years. Oh yeah, that's why I don't remember. But they've done this very it's not complicated if you're doing that research. It all makes sense and it's a logical flow. But oh mercy, there's no way kids will understand this. And so I do show them, but I also talk to them. All right, let's break this down and turn this into things that make sense to us. And oh, she ran away again. She does that.
Do you want me to come sit by you?
No. But it's so, I'll start with kind of the highlighting. Let's look at the corner. Corner tells us our eons. Now it's the largest unit of geologic time. And then from there, it goes to eras and periods. It goes below that. We're really not going to concentrate below that at this time or this level, I should say. But then we put this together. I still don't know if I like this. If an eon was all the years you're in school, an era would be like a school day, and the period would be like a class period. But I don't know if I love that analogy, but we'll use it for now.
It does help kids look at it from a breakdown standpoint, right?
Yeah.
I mean, that's really what it's there
And
for.
that's exactly what I wanted. Something to kind of break it down to relate more to their lives.
Mhm.
And so it's, I don't know, you might have a better analogy that you use. If you do share that, and we might put yours up there instead of the one I thought of that day. But it was kind of like a random thing as you're talking to the students, you could tell they didn't understand. So I was trying to pull an analogy they'd understand. I'm like, okay, this will work for me for now. And then we're talking about timeline. When we look at timeline, we look at things we call like index fossils. Well, that's another vocab word. It's a animal or plant preserved, blah, blah, blah. We know what they are. And so then when you say, well, where will index fossils fall in there? And that brings us to making an actual timeline. You see the picture off to the side here. That's for years I did this with the cash register tape, just like everyone else. And I would, tape it down in the classroom. Kids would walk through and step on it and tear it up every time in between classes and stuff. So I was either taping it back together or stuff like that between class periods. And that got just a little. And so we had the cotton rope. It's just clothesline rope, literally is what it said. And heck, I got these from you, Bill. They were left over from those kits.
Oh, okay.
And so I'm like, well, these are perfect. And so what I went down, and I used to use 2 cash register tapes. I didn't give every group some. I know a lot of teachers give every group one to do them. I would use one on each side of the room and just run it that way when I taught it. But now with the rope, I don't have it consumable, and I can just keep reusing that same piece of rope, wind it up, throw this in a small shoebox, and it's easily stored at that point. But and of course, I mentioned that I've done it with just 2 there. If you have like that advanced class you really appreciate, and then you can have them actually mark out the ropes, the timeline ropes, and prepare those for you. So you have those for each group, which would be kind of nice. And another thing that I did, but I didn't put in this lesson necessarily because I'm not handing out a bunch of fossils. Although if you come here, there's still some in the back of the room. I tried giving away last year, and there's still some left.
Or go find some.
Or you go find some. Go walk through somebody's driveway, gravel driveway. But there's actually the actual fossils to put on the timeline. And so if you have some in the classroom or something, it's kind of nice talking about those. But to make the timelines for each group, it's just about 5 meters of rope, markers, tape measures, all we needed. And we laid down that rope next to tape measure. You can see that's exactly what we've done here. And actually, I have it kind of set up behind me. And then we'll just begin today. And then, I put about 20 meters from the end is where I start with today. And not that I'm preparing for millions of years in the future, but I need something to tie it to. And so I used about 20 centimeters of that on each end. So I can tie it, whether you're tying it to 2 chairs, stringing across the classroom. Here we have the years, we have our lab benches. And so with them, we just stretched it across each lab bench. And this is, then what the kids at this station would turn around and put their cards at this, on this timeline. And that worked really well for us, but we were fortunate enough to have actual lab benches. I realize most people don't. I know when I taught this in classrooms, I'd never had a lab bench. I used either 2 chairs or I used a floor. And, but one thing I like doing beforehand to prepare it is marking the eras for the students. And I put on there exactly how far, the time. You notice, I know Precambrian is not an era. I'm aware of that, but I like them to understand Precambrian. That is how long of a span that is. And so I just do that in pink. And then, of course, Paleozoic, green and blue and yellow. And you'll notice that corresponds with the international chart. And so those are, which I realize the chart, if you go into that, they tell you exactly what hue to use for each one, just like paint chips. I didn't get quite that serious about it. But I just used whatever markers I had. And I just drew a line on them. I drew a black line on it, so I knew where my start and stops were. Then I just took and zipped down the line in a couple spots. You can see it's like banded because I didn't like sit there and color the whole thing in. But so that's how I did that. Then I give them the index fossils. Now we made these little cards up and we pop that open. This is not the right page. This is the right page. This is the 9 up. And then so 9 on a sheet. This is the size I gave the students. I printed these off and then just put them in envelopes. Each group got an envelope. I'd cut them out too. But I tried to line that up best I could. When I did this, you can just use a paper cutter, cut those out real fast. But I gave each group the 9. I stuck with 9, especially since I was teaching this in the middle school and designing it for, introduction. We don't need to go too in depth at that point. If you're teaching high school also, you'll probably go a little bit further in depth and you might have a few more, but I don't know if you'll actually need for an introduction purpose any more than this, in my opinion. I found more than this gets confusing. Then I also made these where there's 2 to a page. And what I did is gave the students the smaller ones. Then I held the larger ones up and I made a demo one so they could see it easily across the room. And so I have just 2 to a page. So I have larger ones. And then what we're having the groups do is just literally if you use that rope on like the floor on tables and stuff, they can just slide it right under it where they think it's going to be. That takes no time at all. It's very simple. They don't have to draw on it or anything like that. I know some teachers use new cash register tape every year for every class. That was just a little bit more of a budget than I had teaching. And this is something it's once you get it together, you don't need extra stuff. But and then that's just what I had them do. I had them predict where they would go, slide the cards where they thought they'd go. Then I had a teacher rope up front. And I would pull up one of the cards and like, where do we think that goes? The teacher rope I would leave beside my tape. And so I'd use like a 50-meter tape I'd have up there beside it. Granted, we're not using all 50 meters for this. You could go down the hallway and do that if you want. But it's just a 5-meter tape we're using, or 5 meters of it. I had it up there. And that way I would walk down with my little cheat sheet, so I didn't have to memorize things. And I'd be like, if we grabbed, the one with prokaryotes, I know I'm 3.3 meters or 330 centimeters from present day. And so we start present day and we go back.
One thing that you did the last time we did this in here,
Mm-hmm.
and I really liked, was you had the kids walk where they put where they put the first one. And it was kind of cool because you would see different groups at different places.
Yeah, so for their predictions.
Yeah, for their prediction. And I thought that was really good because then the kids saw other people and they're like, well, wait a minute, why are they there?
Yeah.
And then when they see where it is, then they're like, oh my gosh.
I did like that too, and that's a fast way. We always want students to share and stuff, but rather than taking time of asking different groups and remember what groups I asked, it was just like, all right, one person go to prokaryotes. They would raise their hand where they thought it was, and they could see how well they lined up or didn't line up, which I don't think they ever did line up anywhere. But it's nice to see what your peers' predictions are.
And you could have you could have like the first person come up to the front and stand where they had it on theirs. And that way it's at the teacher one, and then the teacher can then, however you want to do it, so they predict it.
Yeah, I just like it. I like having theirs. That's why we did. And when I set the student one up in groups in here, I had them all parallel.
Yeah.
So and that's what Bill's talking about there. You could actually see in parallel where they were. So you could see how staggered their predictions were.
If you look behind Steve, you can see all the lab benches, and he just had them, stretched out across each one.
That worked out really well in here. Now, some of the classrooms I've done this before, we didn't really have the space to do more than a couple that way. And so we did, but I would do a couple that way and just kind of divide the things up in the class. And that goes a little faster, but rather than just asking each group or asking a number of groups, they just show me, all right, go have one person go to there and raise your hand. Whatever person was raising a hand in that group, we know that's where they predicted first fish.
Yeah.
And so that I thought worked well. I liked that.
I did too.
The way that came out. And then we would go through that, and then it's like some of these are fossils, and you'll see fossil pictures on there and stuff, and especially if you're using fossils. But the big thing that we want to ask at that point is, well, because someone's going to ask anyway, how do we know how old these things are? And that's where we want to go into, and I know I have the analogy here of using a sand timer, and how you flip that over, you could see the change. Well, fossils, rocks, they change over time too. We don't see that change, but they change over time too. And we can measure that change. And that's where radioactive dating comes in half-lives. Now, for this, we do have, I like using, if you've not used it, I like using the RACES writing strategy that'd be problem 2 for questions. And I got this, it's not that she didn't develop or anything, but I got this from my wife, who has been a classroom teacher for 25 years. And a couple years ago, she moved into, or this is being taped, and I can't remember the name of her title now.
Reading and recovery.
Intervention?
Intervention.
Yeah.
I have like Bill and Sarah both trying to coach me through this here. Love it, baby.
Intervention.
She's moved into intervention, and so she's done a lot of professional developments in elementary, and so she does a lot of professional developments on writing and stuff. So I had her help me with this, and we had used this for an elementary workshop. But I love this at all grades, being able to walk through and help students organize and be able to answer those questions. So that's what this is. If we click on that, it will take us to where you can print this out if you want. Now, some of these you'll see on this assessment one, I don't have on our timeline. Like we mentioned mass extinctions, or I have a bold somewhere in mass extinctions, and I know when we taught it, I always mention it, but I didn't have it on the timeline. And so, but for assessment, I want them, here is a timeline with years, millions of years ago, and I can tell them a T-Rex, you know, oh, here's how big it is. I'm throwing in random numbers. Well, it's not random. It's really how big they are, but you know, 70 million years. So I want to see that T right here, a big T-Rex written right here. You know, a mass extinction event. We have 2 of those that we've listed out of the big 5. And I know if you're like this hardcore geology person, you're like, wait a minute, it might be 6 because some scientists are arguing we're in the 6th great extinction now. But
Really?
yeah. We have so many, and this is the one and only one caused by humans. We have caused, we report over 1,000 species to become extinct due to changes in environmental uses because of us. Not to mention the different ones because of the subtle climate changes and things.
Interesting.
So, but I mean, it's like the KT, that's the one with the asteroid. All the kids are, well, I won't say all, but a lot of kids are, oh, the asteroid that killed the dinosaur.
Right.
Well, didn't really kill them. Yeah, it's
Did it maim them?
well, okay, the ones that hit it killed. Okay, thanks, Bill. But what's crazy about it is when we think about that, why did they really die from that? Because they're cooled down.
Right.
You know, it's like all this debris into the air, so that light wasn't getting through and it cooled the earth. The environment's changed. And that's where they died. When we think of, oh, the asteroid, we think, oh, it's all this heat and flames. And even the greatest extinction event that we've had were 90 what? I have it in here, I think.
It's like 96% or something.
Yeah.
Like that.
Oh, I didn't put the number of how many, but yeah, I was like the Permian.
Mhm.
That was 96% of the species on Earth died in that
Mhm.
2 million year span or whatever. And that's because of the acid or acidic from the volcanoes.
Acidification, yeah.
Yeah, acidification. And so we're changing in the Sarah's world there.
Yeah.
And I think we're rambling. And so, yeah, I'll jump back off that. I'm sorry. So then we went through different standards that could apply. And as you know, it depends on exactly how you teach it on how well they apply. But we could definitely address these particular standards. And I'm realizing that, you know, sometimes elementary's teaching up, middle school's on, and sometimes high school, these fall under. And so we think we could use a lot of this for those. And on the bottom of this, we mentioned half-life and radioactivity. You have a pause.
Before you go to that, are you switching to the next one?
Well, I was transitioning. You just like ruined a perfect transition too.
Well, but I
That was
wanted
gonna be a beautiful transition.
here, you can go back to your
I'm
transition in a
inspired.
second. Are there any, before you transition, are there any questions that people have about what we just went through right there before we move on to the next part?
All right.
Does anybody have any questions? I kind of want to give a little pause there so that if there is questions, we can answer them. We are practicing our wait time as teachers. We are each counting in our head.
Well, I wasn't counting.
Oh. Yeah, you can counting. Start over 1, 2. Okay, if there are no questions, then we'll let Stephen go back to his beautiful segue.
Oh, yeah. Oh, yeah.
And go.
Oh, and at the bottom of this, we mentioned understanding fossils. We need to understand half-life and radioactivity. And to understand half-life and radioactivity, what we have is
a lesson, introduction to radioactivity. So we've created this to help students look at what radioactivity is, the nature of radioactivity. And within this, we're going to have them we have a virtual lab embedded that we're going to go through where they're going to have a chance to collect some data based on placing radioactive sources a certain distance from the detector, using different shielding materials, going over some basic vocabulary for radioactivity, just kind of all of that tied into one lesson. So from this, you know, we're assuming that the way that we've written this, it could be done in about two 45-minute class periods. If you have block schedule, if you have longer class periods, you know, maybe one of those it could. With this one, because there are some different pieces that you can assign to students. If you're interested in answer keys for that, we've created a form. This form, what we'll do is you'll click that. It's just a couple of questions to answer. We'll send out all the links to the answer keys to you. What we like to do from this is we like to collect a little bit of information up front, just so we kind of know, like, you know, that first year, how many students will you be using it with, what schools are using it. It just kind of helps us from there. We would also like to ask for all of these, and for this lab specifically, and then for all of the virtual labs that we have, which, and we might just quickly talk about at the very end of this, that we do ask that if you're interested in these keys, that you not share the keys with fellow teachers, but instead have them also complete that form. It's a really short form, but again, all of these metrics just kind of help us continue using our time to develop new lessons, just to keep sharing those out. So it really does help us, and we appreciate that. So for this introduction to radioactivity, we kind of start with a lecture. So we have this beautiful Google slide presentation. Thank you, Stephen, for this. He's just really glossed this up a lot. It looks super nice. Mine was just pretty much text on a slide, and
It was plain and ugly. I made it pretty, but all the smart words are hers.
Oh. But what we
It had great content. I
like the
Yeah.
I just
Yeah.
get more focused on content, not necessarily as aesthetics. But yeah,
It's
you
pretty.
do such a
Can we
good
see it?
take it to
Yeah.
that next level. But yeah, so we have the link to this. Oh, I guess we already had it.
Yeah, you opened the other thing before.
Okay, here we go. So as we go through this, we do have the link to the teacher page as well. It just kind of circles back to that. This is just kind of an informative. A lot of this information you might already have. It's pretty textbook stuff, but it's all just kind of here.
It's nice for the refresher.
It is nice for the refresher.
Because I was like, all right, explain this to me, kid, because, and you'd think I'd know it with the, I mean,
You know,
grab up courses I've taken in.
absolutely. Sometimes we forget, and especially if you're not
Judge me.
teaching it every day, or it's not something you're thinking about, it's easy to lose. You know, if you don't use it, you lose it. So that's, I've always thought that. So for this, we'll just quickly go through the presentation. Throw out any, if anything's unclear, just let us know. Bill will stop us and we can have some clarifying statements. But, you know, an atom is the smallest piece of matter that still maintains physical properties of a chemical element. Atoms are made up of a nucleus. In that nucleus, we have protons and neutrons, and then we have electrons in this area surrounding the nucleus. And I also like to point out that the plural of an atomic nucleus, we would call it nuclei. And so that's going to play in. It's just kind of some vocabulary, some jargon that as we start throwing these out, I just want to make sure that we've named what these are and explained what these are. Proton, it's a positively charged particle. It has a mass of 1 AMU. I like to use labels. I always think, you know, if you don't slap that label on there, you don't know what you're doing. AMU is an abbreviation for atomic mass unit. And so it's not like it's 1 gram, for goodness sakes, or anything. We're talking about an atom, or actually we're talking about a part of an atom. So it's very, very tiny. And so the unit just is AMU. A neutron is neutral. That's why it's named. It's a neutron. It's neutral. It has no electrical charge associated with, but it also has a mass of 1 AMU, 1 atomic mass unit. So that proton and that neutron are right there in that nucleus. That's where all that mass is coming from, that atomic mass. The electrons technically don't have a mass of 0. They technically do have a mass, but it's so small that especially in the middle school realm, we can just call it 0. And then later, when they get to more advanced chemistry, we can talk about what that value actually is. So electrons are negatively charged particles, and then they orbit the nucleus. An element's atomic number is always equal to the number of protons that it contains in its nucleus. So the atomic number is the number of protons. Here in a moment, we'll pull up a periodic table and we'll kind of see that. But that's the way that the periodic table is organized. It's organized in order by the number of protons, by that atomic number. In its neutral state, which means the element would not have any electrical charge with it, it has the same number of protons and electrons. So in the ground state, in the neutral state, an element has the same number of protons and electrons. So we would know how many electrons it has in that neutral state, also based on the atomic number. Again, you get into more advanced chemistry, the number of electrons can change, and that's chemistry, but we aren't going to worry too much about that right now. So, and we already kind of talked about the next part, the atomic number is how we organize the elements on the periodic table. And so this is kind of a typical block that you might see in a periodic table. We also have a link to, I think, the Royal Society of Chemistry periodic table here. It's also linked back on the web page. We'll go back to that. But typically, you might just have the element symbol. Some of the fancier periodic tables, it'll actually have the name written there. But you really, you know, most of the time you only really need the symbol. The atomic number is usually listed somewhere, and in this case, I think this is from the Royal Society. This is from the periodic table that's linked. We're going to find all of those atomic numbers in the lower left corner. And again, this is the number of protons that each of those elements has. We also see on a periodic table, we see a decimal number. Now, this is where it gets a little confusing. I don't say a lot about this number because this is the average atomic mass. And this is, the idea behind this is actually pretty complicated, in my opinion, for middle school. I think it's beyond the scope of what middle school would need to know. If you're more in the high school realm, the way that you go about getting this is there are a certain number of species of element, we call them isotopes. So they all have the same number of protons, but they have different numbers of neutrons. And this is actually in a slide still on this presentation. It's down a little bit lower. And then you have, some of them occur more frequently than others. And so we call that abundance. And we kind of average all of those out based on how likely it is that they occur on Earth. We average them all out and we come up with, it's an average number, so we come up with a decimal number. This is not the mass number that we will be using for the exercises that the students will be doing, learning about nuclide notation. So learning about the different elements, their mass number, their proton number. We can pretty much ignore the average atomic mass that's on the periodic table. And again, I'm saying all of this for your benefit. This is really never anything I would ever talk about with middle school students. So we'll just continue on here with the presentation and we will talk about what we do want to know. So that is the atomic mass and how it's related to atomic nuclei, or the nucleus of an atom. And we find that, again, by adding the two subatomic particles in an atom's nucleus. So the protons plus the neutrons is equal to the atomic mass. So if we were, for example, if we were looking at an atom of hydrogen, hydrogen is our element, we're looking at one atom of that element. That in this case, we're going to say it would have one proton and 0 neutrons. So the total mass for this atom would be 1. In this case, we're looking at, in this example, in this atom, this one atom of nitrogen. Nitrogen is the overall element, but looking at one atom of that element, this one nitrogen would have 7 protons and 7 neutrons. So when we add those together, we would get an atomic mass of 14 AMU. And again, I should have been labeling that, but then in the notes down below, the instructor notes, I did label the 1 AMU for that, or 14 AMU. Okay, we will have some practice examples that I'll pull up next, but these are every example that we'll see here. The students will have an opportunity to practice that in a page that we've made up. So every element is organized by its atomic number, by the number of protons that it is. But different atoms of each element can have different numbers of neutrons. And so what we want is we want a way to specify which atom we're talking about for the overall elements. And so the way that we do this is we call them nuclides. The nuclide is specifically the atomic mass and the atomic number for that atom of whatever element it is that we're talking about. Each atom has its own mass number. The mass number has to be included with the element symbol. That's really the only requirement of nuclide notation. And again, that's just how we write it out. But together, this information describes that nuclide. It's an atom characterized by a certain number of protons and the atom's mass. We don't always have to put the number of protons because we can find that right off the periodic table. If we have the symbol, if we have the name and we know the symbol, then we can find that bottom number. But we do in every one of these are 3 different ways of expressing a nuclide. And every one of these, we do have to include that atom's mass number. In this case, for example, we don't see the atomic number 3 here, but we would be able to look up lithium on a periodic table and see, oh, that has 3 protons. It has an atomic number of 3. So if we look at an example of this, or the reason why we want to write nuclides in this way, showing their atomic mass and their number of protons, is because we can then easily subtract those 2 numbers, and that helps us find the number of neutrons. And again, the number of neutrons can differ based on different atoms of the same element. So it can have different numbers of neutrons, but the number of protons always remains the same. But the mass number will change because neutrons also contribute to that mass number. So here we have two different examples where we might want to know, so what would the total number of neutrons be for each of these examples? So if we were looking at a carbon-12 nuclide, we would know that 12 is telling us that it has a mass number of 12. The 6 on the bottom is telling us that that's its atomic number, its number of protons. And so by subtracting 12 minus 6, we would know that this atom of carbon would contain 6 neutrons. And here we see an atom of beryllium. In this case, we see this beryllium atom would have a mass number of 10. And beryllium always has 4 protons. It's the 4th one listed on the periodic table. And when we subtract that difference, in this case, they just happen to both be the same. This would also be 6 neutrons. But if we look at a periodic table, carbon, actually, well, we'll look at both of them. Carbon, here we're saying this one atom of carbon has a mass of 12, and this one atom of beryllium has a mass of 10. I'll jump to a periodic table quickly that we'll come back to. If we look at beryllium here, it's saying its average mass number is 9.012. So that's where, when we were talking about, we aren't talking about the average mass number. We're talking about the specific mass number for one atom of that element. This is talking about all elements of beryllium, all of them averaged together. And so in that sense, this mass number is not useful to us the way that it appears on the periodic table. So if you have questions about anything we've said at this point, just send them out in the chat, and we'll be happy to talk
that carbon 12, and I hear carbon 14 dating,
Right.
C14 dating.
Yeah.
And that's just means instead of 6 neutrons, it has 8.
Yes, correct. Yeah. So the only difference with carbon 14, we would change that mass number. Instead of a 12, we call it 14. It would still be a 6 because it's the 6th on the periodic table. But what we've done is we've increased it by 2 neutrons. So it's affected the mass number.
So since it's different, that's why it's unstable?
Yes. And we'll get to
Oh,
that periodic
get to
table in
that.
a minute too.
Okay.
But yeah, I'll show you how we actually found a really neat resource that will show you all possible isotopes for every element on the periodic table. It's an interactive, it's my favorite thing about this whole lesson. Like, I'm really nerding out over this interactive periodic table. But I'll show you where it will designate which of those isotopes are radioactive or unstable. And there's usually way more stable isotopes from that. Bill, did you have a?
I was just going to say, you talk about the atomic number, and we tell kids that that those number of protons don't change.
Right.
For eons and eons, people were trying to change it because they wanted to make gold, right?
Yes.
They wanted, and so I always tell kids, you can't do it, because if that was the case, gold would be worth nothing because everybody would be able to change. Yeah. So, I mean, that's why. I mean,
Yeah.
if they ever forget, all you gotta do is well, we don't have gold everywhere.
Right.
If we did, then people figured that out.
Yeah, you can't, if that number of protons is not whatever it is, it's not that element. It's that's the identifier for those elements. Okay. I think we're just,
What's your last one?
yeah. So then we've already kind of talked about these. It's kind of a spoiler here, but all atoms of the same element, again, always have the same number of protons. They can have different numbers of neutrons. We just saw how we calculate that. And we take that, whatever the mass number of a particular atom is, not the mass number from the periodic table. We've got to be given the mass number for each atom in that nuclide notation. And we can subtract the number of protons, the atomic number, and then that will give us that number of neutrons. Atoms of the same element with different numbers of neutrons, those are called isotopes. Isotopes refer to a set of nuclides. Again, they have the same number of protons, they have different numbers of neutrons. And this applies to radioactivity because every element that occurs on the periodic table after lead, which is Pb, which is atomic number 82, every element that occurs after that is radioactive. And all radioactivity is the release of energy or energetic particles when the nucleus of certain atoms or isotopes breaks down. And so this breaking down of the nucleus is referred to as nuclear decay. So it's decay, it's breaking down. Protons and neutrons are found in the nucleus of an atom. neutrons by themselves are unstable. They need to be there with the protons to stay stable. When the protons are close enough to neutrons, they prevent those neutrons from decaying. But when a nucleus starts to get that imbalance, when there starts to be more neutrons than the protons that are available, so starting with bismuth and continuing on, then those neutrons can start to decompose. They can release energy in the form of light. They can release particles. It just kind of depends on the atom and or the isotope that we're talking about. But that's what radioactivity is. It's that imbalance between protons and neutrons. The effect of radioactivity depends on the type and energy of the particles or waves produced during nuclear decay. And again, it can be an X-ray, it could be a gamma ray. Those are types of radiation that can come from that. It can also be fast-moving particles, for example, like a beta particle, which is basically an electron, or an alpha particle, which is kind of a stripped-down helium atom. It's kind of a helium nucleus that can come from that. So again, these are just when a nucleus starts to decay, it can either give off this energy or it can give off particles. And kind of linking back to what Stephen led off with, that radioactivity can cause damage in materials, in plants, animals. It can cause damage in human tissue. Scientists and engineers use radioactivity as a source of heat for satellites. They can use it for medical imaging, for cancer treatments, but then also for radiometric dating. And I've included a link here to, I think it's the Department of Energy, but it's a really nice informative link of just about radiation in general. And I was able to take some of that information and just put it here just as a quick reference for us. So if we go back to our webpage, that was kind of our just walk through that presentation. There is a guided notes handout that you're welcome to print off for students. If you're walking through it with students, it's kind of just a fill in the blank one. If you complete the request for an answer key, we'll certainly send you the key for that guided notes page. But then also I wanted to share the student practice page with some of those nuclide calculations that we were doing. So that's what this looks like here. They start with it names the element and it just wants them to add the protons and neutrons to find the mass. So they practice a little bit with that. Then they have a couple where they calculate the number of neutrons. So they're given a mass number specific to that element, and then given the number of protons, and they calculate neutrons by subtracting. For 11 through 13, we actually want them to practice writing the atom that's specified as a nuclide in nuclide notation. They can use any of these three forms. So they give an example here, it has an atomic mass of 7 and a total of 3 protons. Any of these three would be appropriate to write as a nuclide of that atom. So then they practice that with 3 of them. And then for 14 and 15, what we're having the students do is kind of check out that periodic table, and I'll go to that periodic table next here, but make a list of isotopes for 2 separate elements, and then write each isotope for those elements using the nuclide notation that they practiced in questions 11 through 13. So it's my favorite part here. We'll go to this. We have a link on how to get there. Actually, if I back up one time here, this is isotopesmatter.com. And I went to this interactive IUPAC periodic table of the elements and isotopes. IUPAC is the International Union for Pure and Applied Chemistry. And IUPAC is really cool because it's where we get all of our naming, and they're kind of in charge of how we name those different compounds, how we name different elements, that sort of thing. But what I love about this, the way this is organized, first of all, it's a periodic table, it's clickable. If we start on hydrogen, what we see here is we have, of course, its name. We see the symbol with the number of protons, so the atomic number. And then we see, so just a little bit here, we see its average atomic mass, and we see the stable isotopes that make up hydrogen. But there are more than just hydrogen 1 and hydrogen 2, which are those stable isotopes. If we click on them, it'll show us the abundance of each of those. So this is, again, more than what our students are going to need, but it's kind of showing us This is the mass of what hydrogen 2 actually is. This is the mass of what hydrogen 1 is. It has their abundance, and then that's ultimately averaged together to get our 1.008. But if we click on more information, every element on this periodic table has this really neat PDF document listed with it, with all kinds of information about each element on the periodic table. Here, what we see are hydrogen 1 and hydrogen 2. These indicate our stable isotopes, and those are listed right here. Then we see some notation, hydrogen 3. This is the half-life of all the radioactive isotopes. So in this case, hydrogen 3 would be considered radioactive. All we know from this notation is that its half-life would be more than 1 year, but then it goes through what those stable isotopes were used, kind of a real-world connection, again, to, in this case, to hydrogen. It says hydrogen isotopes in Earth and planetary science. Talks about primary uses of stable hydrogen isotopes are used in forms of hydrology. We kind of go through here. There's different graphics and things for them. Here it shows atomic weight of hydrogen in river waters, which I think is kind of neat. There's just some really neat things to look at and to investigate. We'll kind of click through a couple of others. If I go back here, we'll look at carbon because, we want to make that connection to radiometric dating because we're talking about geologic time scale. If I click on carbon, I see, again, carbon with its atomic number of 6. Here, what we're looking at are the stable isotopes that they've identified. In this case, most of the carbon that we have, 98.9% of carbon that exists here on Earth, has a mass number of 12. That's kind of our standard. But a very small percentage of carbon is carbon-13, and we would have its mass number here. And between these are both averaged together to get our 12.011 average atomic mass. But if we click on the more information here, we see some other isotopes of carbon that exist. And in this case, we see carbon-14 is, the diagonal lines that are listed here. Again, we see the stable isotopes listed above, and has, again, some neat graphs and things that we can read through, probably kind of where, selected cells of a 30-year-old human determined with carbon-14 produced in the 60s as a result of above ground nuclear weapons testing, which is interesting to kind of read through that. Down below, here it has a picture and talks about variations in the isotope amount ratio of carbon-13 to carbon-12 of marijuana plants have been used to determine whether those plants were grown inside a building or were grown outdoors. And so that's a use of that. I think it's kind of fascinating.
There's talking about marijuana.
Well, it's a resource that's listed here on this, and IUPAC is pretty official. So, but then it also gives some nice information about radioactive carbon-14 as a basis for the radiocarbon dating method to determine ages of carbon-bearing materials. So,
as you were doing this, I was thinking back, and I remember some teachers when I taught middle school that would have kids pick an element and do like a little research on the element. And how cool would this be?
Absolutely.
To have this to be able to go, okay, and then the kids would get up and present on their element.
Yeah.
And they could give knowledge about their element, and what a great opportunity for them to present. But then some great knowledge.
Oh, and I just love it's for every element on here that we have these. But so getting back to what we're asking the students to do is to choose 2 elements. So maybe they choose nitrogen and carbon, but then we would want them to go through and find, let's say if we chose, I guess we just looked at carbon, let's look at nitrogen. If we wanted them to make a list of every isotope associated with that element, here they are. So they could go through and list all of these in their nuclide notation, however they want to practice their nuclide notation. But here is where they find all of those isotopes for nitrogen. So anyways, that's where they find that. It's kind of something fun to click around on to look at. That gives us our kind of basic, this is just another link to the Royal Society of Chemistry periodic table. That's the one that you'll find on all the Purdue websites, especially the Department of Chemistry is the link to this one. But I really liked the IUPAC one as we were going through because it focused on those isotopes. So once we're through kind of the vocabulary, practicing a little bit with what those nuclides look like, we get to the lab. And what we've done together, we went through and took a lot of video and organized it for us in this interactive lab. The link is here. It's also up here. If we go ahead and click, I'll make sure we don't already have it open. What we have is the effects of distance and shielding on exposure to radiation. We start with a little blurb about background radiation. It's all around us. It's always present in our environment. It comes from a lot of different sources, natural and man-made. The natural sources include cosmic rays from space, including the sun, radiation from rocks in the soil, and also radon gas. And the amount of background radiation that we're exposed to varies depending on location. Some places have higher levels, some places have lower levels. If you live in a place with a lot of radon gas in the soil, you might be exposed to a little more background radiation than if you live in places with less radon in the soil. What we can do here is we can download a student handout if that's something that, that you'd like to have students filling out. This can also be assigned virtually. But then we go through, and basically the handout is just a copy of what we're all going to see next here. We start with taking our background radiation counts. And so we see our trial. And what we do is if we click on any of these links that we'll show you here, it's going to bring up a quick video. This is what students would see if they were in the lab using a nuclear scaler. And so what we see is we press the count button, and this is counting radioactive particles. It's counting radioactive particles over a period of time. So we've set this time for 30 seconds. We kind of see here, you know, we stop it before. So it's a 35-second video, but we stop it at 30 seconds. It's important to collect this background radiation initially. This is the background radiation that was occurring in the lab where all of the other samples were taken. If we go back to this, the students would write down that count after 30 seconds. They'd go to the next one. You can kind of just see, you know, what's happening here. They aren't all necessarily going to be the same number because it's real-time data that they're collecting.
Not real-time data.
Or not real-time data.
That was a lie. Quit lying.
Sorry. Thank you for catching that. Not real-time. It was real-time data.
It was.
We're filming it. We're
It's
showing you
actual
what this
data.
was.
It's
actual data.
Not real-time from where they are.
Real time when we did it.
Yeah.
Is what we did, yeah.
Yeah, no, it's
So
right.
what's
I
that?
said wrong. Yeah.
One thing that they can maybe explain to the kids if they want to. I mean, so there it's a Geiger-Müller tube that's collecting this, and the analogy that I've heard is imagine like a trampoline, and you have you drop a marble on a trampoline or a ball of some sort, and every time it hits that, the trampoline moves.
Yes.
So it detects that motion. So every time a particle hits that, it detects it, and then it hits it again, it detects it. So every time a particle hits that trampoline,
Okay.
that's the count that you're getting. And so that way the kids understand it's not just some random thing out there that's doing it.
Yeah.
It's actually a particle hitting that.
Yeah. They average all of those, they get them, they record them, and then they average them. So they watch the 3 videos. We did this 3 times. They get an average value.
In this handout.
Yeah, that's on the handout. But then they use that average value as they continue on through this. And this is really important to remind them as they're doing this. Every count that they take, they want to make sure that they subtract whatever that average count was, because we're in the same lab taking all these samples. These were all done basically at the same time, right? Yeah, right across all from
They'll do them all at once.
And on that day, that was the radiation count in that room for the background radiation. So we're correcting that value. I think there are some really interesting discussions you can have just about data collection in general and why it's important to factor in things like that, just so your data is all kind of usable for that we've factored some of that background stuff out. In this section right here, we're looking at how distance affects exposure to radiation. So I'll click on one of these, but you're going to notice there are these shelves. In this nuclear scaler that we're using, there is the detector kind of at the top, and then there is shelves underneath it. So we're at the second shelf from the top for this top row here. Then we move it to the third shelf. So we move it a little farther away. So by the time we get to the 6th shelf, That's the farthest position away from the detector. So we've increased that distance to our max possibility for that nuclear scalar that we have. The other thing that I'll point out is that we have sources, alpha, beta, and gamma sources that are used. Bill and Stephen went through and measured all of those. So again, there was a lot of video to edit for all of this. It was a lot of trials to do for all of this, but it's a really cool resource to have. So if we go for this first one, we'll just show the second shelf. We'll show how these all differ. We started with beta. And again, showing beta source shelf 2, we start that count, and you're going to look how different that is from when we were taking our background count radiation. I think all the background radiation is like a 9 and an 8 and an 11, I think, and it averages out to 9 or something. And then we see, so when we're close to that source, we're at the second shelf away from the detector, in about 30 seconds, we'll just see what our count is here.
Feel free to like that video.
Yeah, right. So we're looking at a count of 347-ish, 347.
Yeah.
But then we have to make sure that we subtract off whatever our average background was, and then we record that in the table. So there's beta. Then if we look at the difference, so how does alpha compare to this? Okay, we see that alpha source there in the corner. And again, these are all the blips that are, and the detector's counting. They'll explain the trampoline analogy. There's not an actual trampoline in the nuclear scalar, but it's a good analogy for how they're
It's like
thinking about it.
anyone.
Yeah.
It is black.
Yeah.
Not all trampolines are black though.
The neighbors is. We should go a bunch of marbles for the neighbors, just throw them
That'd be fun.
on the trampoline to video.
Now here's my here's something that I think is good to kind of point out here. So here we see a count of, we're going to say at the end of the 30 seconds, like 9. Oh, actually it looks like
9:30.
9:30. Okay. Again, we would subtract off the background radiation, but Bill, I'm going to put you on the spot a little bit here. Does that mean that alpha is more dangerous than beta? So here we have a count of 9:30 where the beta source was only giving us a count of, I forget, like 340.
Yeah. So, and so the answer to Sarah's question is no. It just means that this one is newer and is giving off more particles because it's fresher at that point, is really the word I'll use. And then as we go through and it starts to decay more and more and more and more, these numbers on, if I kept that disk and I did it again and again and again for the next 6 months, by the end of the 6 month, that number would be way less.
Okay.
So it's just, it has nothing to do with how bad it is or how dangerous. I don't know if dangerous is the word, but if you do the next one, do the gamma.
Let's get serious now.
That's right.
This is why Bill looks like the Hulk.
Our gamma source.
Green, see?
Yeah, okay, green like Bill.
G for green.
So when we press that count button, the count starts over again.
Yeah, so it's doing 30 seconds every time. But you can see this is just shooting through the roof.
Right. Now I've used, so I used to use nuclear scalars in my classroom with them. I have gotten the scalars before where the gamma source, I think the students thought, oh, well, this isn't that dangerous. This is probably not as dangerous as alpha or beta because it was probably at the end of its life.
Yes.
But then I think where we'll really see this come into effect will be the shielding lab then that we'll see here in a minute. So anyway, so we get our counts again. Remember, this is an impressive count actually, 9,639. Again, we correct for background radiation with that. But let's compare that to our 6th shelf.
Yeah.
So now we'll go back. So remember, beta was I think 340 something.
3 something.
Yeah.
Yeah.
So now we move it the farthest distance that we can away from the detector. There we go. Shelf 6, beta.
In these shelves, how far is it from the second one that
A
we.
couple
I was
centimeters,
gonna say, no, yeah.
maybe not even
I
that.
don't even think it's an inch. I mean, it's.
Oh, a total,
Total.
total from there?
From 2 to 6. What would you say that is?
Oh,
2
yeah.
inches, 3 inches?
Yeah, probably 3 inches.
I was thinking between each.
But yeah, in between each
Yeah.
one. So
couple
yeah,
centimeters Each one.
but I mean, already it's done. There's a count of 48.
Okay. Minus whatever background is, 8
Yeah.
or 9 from background. Compared to 347, we see that distance really does a lot to
I think that's what the most impressive thing about this whole thing to me.
yeah,
Is showing how a little bit of distance from
can
a
be
source
Yes.
is really drops things down.
yes. Okay, alpha, I think we were closer to 900, I think, in that second shelf. So we'll look at alpha here for the sixth shelf, so much farther away. And we'll start over. We always start over when we hit the count button.
I mean, we haven't even hit background radiation yet.
Right.
There's background radiation.
Comparatively, the alpha particle is very large compared to the beta particle, and then gamma is actually a form of light, so it's not a particle. Yeah, so this is very, very low. And again, that distance really mitigates the radioactive exposure, radiation exposure. And then looking at the gamma in the farthest position,
And what was it first time, like
like
4,000?
9,000.
Oh, was it 9?
600,
Oh,
yeah. It
I
was-
forget,
Far right slope down.
but clearly you can tell already
Yeah.
that that's not.
Need a little more than distance if you've got gamma radiation. Now, it is interesting that it is a gamma source, and that we can have access to the gamma sources, even though it.
And
Yeah.
and actually, if a teacher out there, if anybody out there really wanted to buy, you could actually purchase these. There's a place called Spectrum Techniques in Tennessee, and you can buy them. It's not regulated, and because the amount of radiation is so small, it's not. You know, in the years we've been doing this, we've had teachers who borrow the equipment, and we've had people pregnant and worried about it, and they don't need to be. Even kids, I mean, even if a kid ate one of these,
Right.
it would
choking out.
it would more of a choking hazard. It would go through them before it would do any damage anyway.
Right.
And even if it got stuck, we're talking such low doses anyway.
Yeah.
We still don't want to eat them though.
No.
We don't encourage that, by the way. Disclaimer. Please don't eat the radioactive sources.
Right. But before, in the second shelf position for gamma, it was upwards of 9,600 for a count. In that sixth position, it's still high, but much less than 9,600, or whole power of 10 less than that.
Yep.
So there's a whole table full of data to collect for each of these sources, and looking at distance, how it affects exposure to radiation. The second part of this lab is how shielding affects exposure to radiation. And I will go ahead and say that for the alpha, beta, and gamma, that we are just repeating the same videos from the first table. So when we were looking at distance from the second shelf, we want kind of a baseline. So where we don't have any shielding at all, this is just kind of a reminder of what alpha, beta, and gamma would look like at that second shelf position. And then what we've done is we've kept each of these sources at the second shelf, but in between it, we've placed a
The first shelf.
on the first shelf, yeah, we've placed a piece of material that's listed here, exactly what that piece of material was. So if we look at, again, the beta was around 340 something, alpha was around 900 something, gamma was around 9,000 something. So if we compare that, if we have a piece of paper shielding beta from that second position, we'll kind of take a look at what it does. There's our start point when we hit that count button.
Can't decide if I want to root it on or
Yeah.
stay back. I can't decide here.
And you do have music playing on this, don't you?
Yeah, the
There's some-
sound is shut off.
No, I know, right, but there's, I just want to tell the teachers, we got a little background music.
Yeah.
So almost a third less. Just that plain old notebook paper is protecting about 2/3 of the radiation that we would have got without it. If we look at the alpha, again, this is at the second shelf, but with the notebook. Oh, wait a minute.
No, yeah,
You can pick that.
there we go.
Paper shielding.
Yeah, yeah.
Okay,
Got a little-
there we go.
Oh, you were saying something. You're talking.
I
Oh,
think,
was I?
yeah.
Yeah, you were talking and I left that part in where
Okay,
you were explaining it. You're explaining that this is alpha down there or whatever.
and once again, remember the background radiation's right around 9,
Mhm.
and just a piece of paper between the alpha and the
Yeah.
Geiger Moller tube is pretty much enough to block it all.
So that's exactly the case. And I want to point that out. I think the average background radiation is 9. So you'll get this situation for a couple of these where what you're measuring is actually less than what the background radiation is. And that's okay.
It's stopping it.
It is. It's not going to be a negative number. That's just going to be a 0. That in this case, we're really probably only measuring background radiation because your skin, a piece of notebook paper, can block alpha particles, and those are easily blocked. They're kind of large lumbering particles compared to beta and gamma rays, and so
They're like pills.
and so in this case, this is really the alpha part. The alpha source is not contributing any radiation at all. So the kids don't have to worry about putting a negative number. That feels weird to me. It would just be a 0, that it's not contributing any. And then we'll take a look at gamma with the paper shielding. Yeah, there's a little bit of introduction to this, but then we do count. Now, this is much more interesting, but it's also gamma radiation. Notebook paper is not going to do a lot to save you with. So
Arena paper is not going to protect you against
Yeah.
gamma radiation.
you need a little more. Although it's not quite at the 9600 that it was, but it's still pretty accurate. So again, we want to subtract off the background radiation, so we're sitting right at 2800.
You sure it's 9600?
I think it was. Yeah. And then if we compare that to any of these, we can actually look at the gamma with let's see with thick lead. Gamma with the thick lead that we have. What does that look like? So again, we've got that gamma source at the second shelf. We have this thicker piece of lead compared to a thinner piece of lead. I don't know exactly how many millimeters.
Yeah,
it
it
is,
doesn't
but-
matter. I mean, it's
Stops it.
And so this is a great time for you teachers to talk about when the kids go and they have x-rays done at the dentist and they put that lead apron on.
Mhm.
That's why they do it, is to block radiation
Yeah.
from them.
And distance.
And-
And that's why they step out.
And that's why they step out of the room, and they don't have to wear it because they're outside the room and there's a wall usually between them and all that stuff.
Yeah,
So,
that's a good, yeah.
Yeah.
Great point.
Because with that cone that spreads out, we did it.
I was just thinking, oh, we
That's
should
that radiation tech.
want to add that in as a
we'll have to add that in.
resource as well.
Yeah, we did. She explained all that. That was really cool.
Yeah, it was. So there is our data collection lab. What we love about this, I did this lab in the classroom with the actual nuclear scalars. Because I live pretty close to Purdue, I had an established relationship with Purdue. I was able to borrow them at times. Not everybody is close enough or has access to get these. So what's so great about this is you can just assign this lab. It looks exactly like, I mean, this is what it looks like, and you're seeing the exact same readings that you would get if you were right there in the lab doing it. We have the handouts that they can collect that data from. So we're really excited about this resource, just to be able to have students be able to collect that data and then answer some questions about what it is that they're seeing. Speaking of um, interviews and things with people related to this material, and we've identified we're going to add one more now that we've just remembered this.
The note down there.
Yeah. So we'll get, I think, Leanne's interview on here, but we do have a handful of others that are kind of related to this radiometric dating, to carbon-14 dating, to stable isotopes. These are all scientists that we know, that we've worked with, who describe a little bit about the research that they do and how it involves this. It's in a podcast format. Students could choose to either watch the YouTube video if they're interested. Actually, I think Daryl's we don't have.
We did have forwarded video.
Yeah, it's audio only, but we still have it on YouTube. But we also have a link to our podcast episode. So the audio only, depending on what you need. And we have some guided listening questions. So the idea is that students could choose one, or you could assign one, or all three. And that they have some questions they can be listening for to kind of help them stay focused. Sometimes it's easier, might have it playing, at least for me. It might be playing, but then I might start thinking about something else. So these questions kind of help you stay focused for that. And then I'm still working on a couple of questions for the measuring radioactive isotopes episode, but it'll follow the same format that these other two do. And then we'll have keys that we can supply to you for each of these. And then as an extension activity, and then we'll have a little more to say at the end of our recording once we stop recording about this. But if you would like to investigate everyday objects, like radiation found in everyday objects, these are Geiger and Muller. Bill, you want to talk a little bit about this? I feel like you know a little more, maybe.
Yeah. Bill is the one that did this.
Yeah.
Sure. So, I mean, they have these radiation detectors, and you can get, I mean, they're all over the place in price, but basically it's the same thing as what you saw with what we showed earlier, but not as high tech, not as accurate, but it still does what it needs to do. And so what we did was we actually took this and
Can't watch it.
oh
Yeah,
that's all right.
Yeah.
You can put different radioactive sources on top of it. I think that's a Brazil nut sitting on there right now, and Brazil nuts give off quite a bit of radiation due to their tap roots being so far down. But also mantles for lanterns give off radiation, and so do old Fiesta ware, the orange Fiesta ware. But you can also use fire detectors. So fire detectors also have, and that's why you have to replace your fire detectors, is because they have a half-life of radiation, and after 12 years, you have to replace them because it's no longer usable at that point.
That kind of is like our sources that we see, right? You have to replace those alpha, beta, gamma sources
after so long.
Same, yeah.
So you can use this handheld to do, and you could set the pieces on top of it and hit collect, and then you could actually move them further away, and so you could look at distance, or you could also put pieces of paper or pieces of plastic or something to block the radiation and look at those as well. So you could have these set up in a classroom and make it a station, however you want to do it, and have kids be able to see physically how to do it without mind. So here's the difference. The ones we showed earlier, they're like 700. Well, last time we bought them, they were like $790 a piece. You can buy one of these for like $60.
Oh, nice.
So that's a big difference.
Yeah.
And so if this is something you're going, boy, I really would like to do this, this is an option.
This this short video you'll be able to click on. It's pretty short. It's under a minute, right?
Yeah.
That we can click on there, and it shows exactly. We have a little technical issue trying to play those short videos from this laptop specifically, but it is certainly up on our channel and it's off. It's linked right here. So if you're curious, Bill did a really nice job kind of setting that up and showing.
And Steve did a great job of taking that and making it a very useful video. I mean, it really explains everything that you can do in a very concise time.
Yeah.
Take 1 minute, check it out, and don't forget to subscribe.
And like.
Yeah. Tell your friends. So here we just have the links. This is the IUPAC. You can get to the IUPAC periodic table from there if you're like, oh, I want to go back to that really cool interactive periodic table. It's right there. And then again, links to NGSS standards. I have both middle school and high school. I didn't feel elementary was appropriate for this, but maybe actually I didn't really love it, but yeah, probably not. We also included, and you have this listed. I don't know if we talked about the cross-cutting concepts.
Oh, it's up in the corner.
Yeah.
Mention it.
See, we've gone through and identified a few cross-cutting concepts for this as well, and science and engineering practices. And so if you need any of those to help, if that helps with your lesson planning, lesson writing, different things that you might be asked to do or to submit, feel free to use any of this that might be helpful to you. Okay.
Half-life.
Yeah, well, do we want to do questions before we
Yeah.
segue into?
Yeah, I think that's a great idea. If there's questions about what we just talked about, went through, type them in the chat. We'll give kind of a pause here. I know you guys would ask them if you were going, but you guys aren't all sleeping, are you? We hope not. Come on. Okay, if there are no questions, we'll go right on to what the heck is half-life?
Oh, half-life. All right. So
Like, did I type that? Oh.
I'm 56 years old. Have I hit half-life?
This is getting awkward.
This is not written to be a virtual lab as the nuclear scalar lab was written to be. So there was a lot of work that went into developing that distance and shielding lab, and it's an awesome resource. If I was still in the classroom, I would be using that every year. I just think that would be so convenient to assign, to get good data from. This is going to be a different change of pace. This is more hands-on. This is the hands-on activity, and we're using a fabricated radioactive element. So we're going to call it penium. And there are many, oh, thanks, Kathleen. I just saw your remark call up here, but we're going to be simulating the randomness of decay in radioactive atoms.
And as a disclaimer, you used this in the classroom.
Oh, yes.
But
Yeah.
you have no idea where it originally came from.
I did,
Trying to find it, we both tried to figure out where the original source was from.
Yeah.
And there are like thousands of variations of this out there now.
It didn't even hit me until last week. And I started like, actually, maybe this is somebody's. And we started Googling.
We couldn't figure
I couldn't pin it down to any one person's. I don't know where I got it from, to be honest. I just know I taught for
Just full disclaimer.
like 15 years and I don't remember where I ever.
Like my grandpa developed that. Don't be offended. We're not trying to take credit.
Oh, we're not trying. We're not charging anyone for it. We're just, this is our interpretation of it. So, so this is going to help us simulate it because we certainly don't want kids handling really radioactive atoms that would decay right there in class. That's kind of dangerous. So these are the materials that we need. I used paper box lids. So when you get like a case of paperines that come in, yeah, you can just get the lids. We want to draw lines across the lid about 3 inches apart.
Just like we did the tray in the picture.
Yep. Stephen.
Sarah was obsessed. She wanted to use box papers. My wife was collecting all these paper box lids.
I appreciate it.
And I'm like, why are we doing that? We have trays.
We had trays, and I'm going to be honest, Stephen, that's a much better, probably more sustainable idea.
This is recorded, right? Mine, it was good.
I just stopped it and started it.
Thank you. I appreciate that. But I will tell you, the paper boxes, I mean, I kept those on top of in my lab for a year. I mean, like more than a decade. Like I would have these paper, I just get them down every year, dust them out a little, and then we just keep reusing them. So whatever you have that's going to use is going to be great. But the idea behind this is that we're trying to figure out how on earth do we even know which atoms are going to decay, and how can we figure out what half-life is? And so the idea behind this is that we have this cup or some kind of container that you can sprinkle things out of. I use pennies because that's what I had, but you could use little like plastic discs, like bingo chips or something. You could use anything like that. And you sprinkle those out. And in the very first trial, any that land on the line, so even if they're touching the line, it's kind of your discretion. that the very first time you do this, so you sprinkle out all 100 pennies and you go through and you collect all the ones that have landed or are touching the line, and you make one stack. Now the instructions tell you to put a 12-inch piece of masking tape right at the top of the tray. And that's so that you can line up your pennies after each trial. So the first trial, you're going to have a really impressive stack of pennies because you have the most pennies possible. Yep, and it's kind of just right down here. In that third picture, you're going to see after 3 trials, after 3 counts. Each time that we sprinkle it, we call it a minute, just so that we can, yeah, it takes more than 1 minute, but we're trying to get some data that we can use to do something with from here. So the very first, we have 100 pennies to start with, so we're going to have more chances for those pennies to hit a line. So we'll have this nice big stack. We put the remaining pennies back in the cup. We sprinkle them again. Again, we collect all the pennies that touch a line. We stack those in the second stack. It's going to be significantly a shorter stack. And then it should go shorter, shorter, shorter. Some of them might be, you might have a couple trials where like they stay kind of the same number, and that's normal. And at the very end, it should finish up. You keep doing this until you have like 0 or 1 penny left. And what we're doing here is we have a data table where we are recording how many are decayed. So the decayed are the ones that touch the line. And then we subtract that from whatever we had at the beginning. So like here we had 100 at the beginning. So we subtract off the 21 and we had 79 remaining. So then the second time that we do this, out of the 79, I had 16 that touched a line, and then 63 remain. The next time it fluctuates a little. This time I actually had 17 that touched a line. So okay, it's a few more touched the line. And then you have less and less and less remaining after every trial. When I did this, I got down to 0 pennies left after 14. So probably within about 15, we'll call them minutes, 15 trials, you should be down to 0 or 1 penny. If not, you can extend it. But then what we want to do is we're going to go back to the web page here. So that procedure, I just kind of walked you through what that was. But now we get to the data analysis. And so we have a link to a sheet of graph paper that's already kind of set up for students to graph. It prompts them to label the axes. We think about that the very first point, if we think about it as an ordered pair, would be before we actually do any of the trials. At the very first point, at time 0, we have 100 pennies. So that would be one of the very first points that we plot. And then from there, all of our X values are, we have them listed on this data table. Again, we have a blank data table link that students can put their data in, but all of your X values are going to be considered our minutes, our time. And then it's the pennies that remain that we use as the Y of that ordered pair. So the decayed atoms, that kind of, what that does is it gives us a nice visual, again, lined up at the front of our tray. If we go back up to this really nice picture that we have, these will be all of the decayed atoms. The decayed atoms give us that instant visual that we can see if we stack them up and just kind of keep track of those after every trial. But it's the remaining pennies that we'll end up using as part of our ordered pairs, the X comma Y. When we do that, it explains that we're going to draw a smooth best fit curve through all of those data points. So we have all our data points kind of plotted, and then we want to do that curve. And I'm going to show you what an example of this might look like. So the data that I had showed from the data table, this is all that data plotted. So again, the 100, that was before we did any trials. And down at the bottom, you'll see the minutes. And then at 2 minutes, we had about 63 remaining. At 3 minutes, we had about 47 remaining. And so we've kind of, and then we made this really nice, smooth, best fit curve through that. It doesn't hit every point, but remember, it's a best fit, so it doesn't have to hit every point. And then we have this kind of strange line here. And the instructions for that are, you go to the point on the y-axis where your remaining atoms is half of where you started at time 0. So half of 100, we started with 100 pennies. So we want to go to the 50 on the y-axis, and we want to start at the 50, and we want to draw a line parallel to the x-axis until it reaches our best fit curve. And once we reach the curve, then we draw a vertical line down all the way to the x-axis. So again, if I pull that back up, here's my 50. I draw a line parallel to the x-axis until I hit the curve. I go straight down, and that's our half-life. So this is a really nice way, first of all, that it gets students collecting data. It's something hands-on. They're in control of what that is. Their data will definitely be different than this example that you see here. They're going to get different numbers, and that's all right. But every time we do this, and actually when we did this and we plotted it, I saw it kind of made me laugh because for years, yeah, that's exactly where that half-life, it doesn't matter where your data points fall, you're going to get that half-life of about 3.1 minutes every time, no matter what. That's just kind of how it
Really?
turns out. Yeah, for years and years and years, I did this and it comes out. That's just what it is.
Which makes sense because your penny's a certain size, you've got
Yeah.
a certain amount of space.
Yeah.
So regardless, you're still gonna, that's cool.
It's really cool. It's neat to see this if you
Yeah, it makes
start
sense.
doing this activity and just for your own knowledge, like you start tracking it every year. It's like, yeah, 3.09 or 3.1, or sometimes you'll get a 3.3. It
Right.
kind of depends, but it's always right around that 3-minute
Makes sense.
half-life. And I like that. That's a really good model for real life. Half-lives are known. We know what those half-lives are for a lot of different isotopes. It'll give that in that IUPAC periodic table that you have. We know what the half-life is. And because that's a known, that's our absolute dating, and that applies back to our geologic time scale. That's how we know the age of these things, is because of the half-life of carbon-14, because of the half-life of uranium-235, that we can go back and we can backdate what those are, what those samples are based on them. The other thing I want to point out, and I feel like this lesson doesn't necessarily get into it, but that once an atom decays, it's still there. It's not that it disappears, that it's just transformed into something else. So it's given off some radiation, and many times that's a particle, like an electron, or sometimes a proton, or sometimes a couple of protons if it's an alpha particle. And so the element itself might change because it's a nuclear decay. The element itself might change, but that the particle is still there. It just doesn't have the same identity. And so it's not like it just disappears into thin air. The material is still there. It's just not that radioactive particle that it was to begin with.
And I think kids have a hard time with this because when you hear the word decay, they immediately go to an animal.
Yeah.
I mean, and so then they see an animal on the side of the road, or an animal that, and eventually after a while, it's not there
It's
anymore.
not there anymore, but it
is still there.
is
Right.
something else. And I think what I did to kind of point this out, and I think that's why it's so important to have them stack those pennies there. Those pennies are still there. These are the decayed pennies. They didn't go anywhere. They've just transformed into something else, but they're still there. It's not like we get rid of them.
Which goes back to the conservation of mass, right?
Yes.
I mean, so
Awesome.
still it had to go somewhere.
Yep. Yep. And so a lot of times what goes somewhere is that energy, whether it's those particles that go somewhere, and those particles are mass. And so, yeah, conservation of matter, conservation of mass.
Yeah, that's cool.
So we have some discussion questions then from that. And again, we have the opportunity to request a key. For this key, I can't really tell you exactly the numbers that the kids should get for decay because it's gonna be different. But what I'll do is I'll share that sample data with you so that you kind of have an idea. And then those discussion questions,
Oh,
I'll have some suggested responses for that.
what just happened? I did not. Did it just, we're still going?
Still going?
Oh,
Okay.
no. Oh, gosh.
It's not built off.
I just killed it.
Oh.
Okay.
The connection for
Oh, thank you, Shauna, for that.
conservation, yes.
Yeah.
Yeah.
And I want to say the tray, the hole in the end of the tray,
Uh-huh.
and you already have increments, so that makes a great erosion tray. So you're different using erosion, so if you're mounting on there,
Multi-purpose.
that's why the holes are in those trays, so the water drains down. Just
That's a
it
great.
shows poor man's stream table, but I've fought with them for
It works.
years. I put the holes into the trays. I used them as poor man's stream tables, show erosion.
Okay.